Okay. All right. So I'll proceed to speak about spectral theorem. All right. So let me address the purpose of this section. All right. In chapter 6, T is an operator. Right? So suppose T is a linear operator on an n-dimensional vector space over a scale field, either real numbers or complex numbers. Right? So T has a diagonal metric representation. Okay. If and only if there exists an eigenbasis for this vector space, associated with T, i.e. We have T ui equal to lambda I ui. Right? So to have a diagonal representation, diagonal metric representation, then we have to prove, to show there is an eigenbasis u1, u2 up to un for this n-dimensional vector space V associated with this T. Means that there are eigenvalues lambda i's there, and TUI equal to lambda IUI there. Now in this section, right, T now is a linear operator on an n-dimensional. Now this time, in addition to have a vector space structure, we have an inner product. All right, so we have inner product vector space V over F here. Right, so right. So we want to know okay, so linear. So we want to find necessary and sufficient condition for the existence, okay, of an also normal eigenbasis for V associated with T, i.e. that T ui is equal to lambda I for all. So the additional requirement is that we want our eigenbasis to be orthonormal. Okay, so this is because we are talking about the inner products. So we have inner products. So we can have the concept of orthogonality. And to have an orthonormal basis has a lot of advantages in our development of results in inner product space. All right, so that is the purpose. All right. So we'd like to know the necessary and sufficient conditions to have such an orthonormal eigenbasis. All right, so so now we have a lemma saying that so suppose so V is an n-dimensional inner product space over F and T a linear operator on V. Okay, so now so there exists an orthonormal eigenbasis for V, okay, associated with T, i.e. T ui to the lambda I ui with lambda i's not necessary, so not necessarily distinct, right? So this is our purpose. So if we have an orthonormal basis associated with this linear operator, means that we have the eigenequations for the basis vector here with corresponding eigenvalues lambda I. And these eigenvalues not necessarily distinct because we have n eigenvalues, right? Lambda 1, lambda 2 up to lambda n. Not necessarily distinct. Then if and only if so they are scalars lambda 1, lambda 2 up to lambda n in F, not necessarily distinct, and so we have scalars and also normal say also normal basis B for V such that the Tx can be expressed in the following way. Okay, so if we can find an orthonormal eigenbasis, then we can express the linear operator T, okay, by using this sum here. Okay, and the lambda i's are scalars, and U1, U2 up to UN form an orthonormal basis for the V. Okay, and we have that. So you see that the T has a very simple representation in this format. Okay. All right, and so there is a remark to say, because that the scalars, you know, actually the scalars, they are so okay. All right. So maybe I first give a proof before I have a definition. Have a remark. All right. So now, because this is an orthonormal eigenbasis, of course, it's an orthonormal basis, of course, already here, and we have lambda i's, so lambda i's are scalars. Okay, so we only need to prove that the linear operator T has this representation. Okay. Now, so since is an orthonormal basis for V, then we have every vector in capital V can be written as a linear combination of a UI, okay, and the coefficient is actually the projection. Okay, so this is actually a projection into the direction of UI. So this is a projection there. Okay. All right, and so this is implies that Tx okay, and the bilinearity of the T of the linear operator TUI, and the TUI has the eigenequation here. So this is okay. So we have done. Okay. So immediately we have this representation. The other way is that if we have scalars lambda 1 up to lambda n, not necessarily distinct, and we have an orthonormal basis for that, for V with this representation. So we have to show that UIs are eigenvectors corresponding to eigenvalue, and okay, I'm sorry. We have to show that we have the eigenequation like this one. But that is simple, right? So we look at Uj. So for all j from 1 to n, we look at the TUJ, and this is lambda I, Uj, and the UI here. But since this is an orthonormal basis, so this inner product is the delta function, delta ij, and the ui, and for delta ij is 0 if I not equal to j, and the delta ii is equal to 1, so this is equal to j and j. Okay, right? So we have an eigenequation here. So this implies that lambda j is an eigenvalue of t, and uj is an eigenvector of t corresponding to lambda j. Right, and so this is implies that is an eigenbasis for V associated with T, and we have done. Okay. So the existence of an orthonormal eigenbasis associated with T is equivalent to having this representation, such that the lambda I are scalars and the UIs form an orthonormal basis here. Okay. Right. Right. So maybe please see the remark after right. Okay. Yep. Because my time is very tight, so I skipped the remark. The remark just explain why we call this as a spectral decomposition. Okay, so it's called spectral decomposition. All right. All right, so now assume T has a spectral decomposition. Okay, because our purpose is to try to find necessary and sufficient condition, right, for the existence of an orthonormal eigenbasis. And the existence of an orthonormal eigenbasis is equivalent to have a spectral decomposition here. Okay, so we investigate some necessary condition, some consequence if we have spectral decomposition. Okay, so that is the approach. Okay. All right. So assume we have spectral decomposition. Right, and where lambda 1 are scalars in F. Okay, as we know, not necessarily distinct, and we know that U1, U2 up to UN is an orthonormal basis for V. Okay. And we also know then T Uj is equal to lambda J Uj for all. Okay. Okay. So from this spectral decomposition, we immediately knowing that this scalar, the lambda are eigenvalues, and UI are eigenvectors corresponding to eigenvalues lambda I. So we have that. Now we look at now we want to know if T has a spectral decomposition. So what is the adjoint of T? Okay, so we want to know that, and so we will investigate. Okay, so now we investigate this inner product, and this one okay. And so by linearity of inner product for the first argument, so we have lambda I, and then this is x ui, and this is ui and the y. Okay, so we have this one. All right, and now, so we have two possibilities that we now look at as the scalars, and we want to put into here, into the second argument. Okay, move into there. All right, so we have this one, x summation. Now, if we are in the complex case, then we have to take the complex conjugate here, and complex conjugate here, and the ui. Okay. So if f is equal to c, and lambda I, ui, y, if f equal to r. Now, and so here, x summation I from 1 to n, lambda I bar. Okay, and here is y, ui. So if we exchange the two arguments, right? If you change them, then you have a double bar, and this is just the inner product here, and you have ui. If f equal to c, and this is x, and this is lambda I, and y ui. Okay. Now if you change them, because by symmetry, for the real inner product, then you can exchange them, right? And the ui, if f equal to r, and this is equal to x t dagger y. Okay. By definition of t dagger, the adjoint of a linear operator t. Right, so this is equal to this one. But by our calculation, we see here. So from this calculation, we know that. So we know that t dagger of x is equal to 1 to n. And the lambda I, x ui, ui, if f equal to r, and the summation lambda I bar x if f equal to c. Okay, so from here, so this is, because this is true for all in V, okay, so we have that the case. All right, and so when f equal to r, in the real case, we see that t dagger is equal to t, because this is exactly t. Okay? Exactly. We assume t has a spectral decomposition, so that so t dagger is self-adjoint. All right, and okay, so t has a spectral decomposition. So if t has a spectral decomposition, then in the real case, t must be self-adjoint. I'm sorry. Okay, so t must be self-adjoint. So we find a necessary condition here. And later on, we will show whether this is a sufficient condition for the real case. Right? Now, for the complex case, For the complex case, that of course T dagger is not equal to T in general, because if the eigenvalue lambda I is not real, for example complex, then the complex conjugate will be different. Okay. But a T dagger and we find that this is the J, Uj. Okay. So this implies that Uj, so implies that lambda J bar is an eigenvalue of T dagger, and Uj is an eigenvalue, eigenvector of T dagger corresponding to lambda J bar. Okay. All right. So T dagger and T share the same eigen vectors, but corresponding to different eigenvalues, right? So if lambda J is an eigenvalue for T, then lambda J bar will be an eigenvalue of T dagger. And furthermore, all right, we look at the composition of T dagger and the T. So this is T dagger and the Tx. Okay. Right, and so T dagger summation lambda I, and so this is okay, and this one lambda I bar, because T dagger, so Uy is an eigenvector of T dagger. So this is, so again, with eigenvalue lambda I, right? And but if you do it again, but reverse the order. So if we look at the composite of T and the T dagger, so this is T dagger. We see that they are the same. So that T dagger, T and T dagger. So in terms of composition, in terms of the operation composition, T dagger and T commute with each other. Okay. All right, and so in this case, T is called normal. Right? So any linear operator has this property is called normal. Okay, normal operators. All right, and example. All right, so on Fn, on the n-dimensional Euclidean space, we define Tx equal to Ax so where Ax and n times n matrix over F. Okay. All right. So T is the linear operator on Fn, and then so this T must have a metric representation we call A, and this metric representation, of course, relative to the standard basis, as we know before. Right. Okay, and in our previous, in the previous subsection, or just say in subsection 8.1.2, the dagger, the T dagger actually is equal to the Hermitian, the conjugate transpose of A times X. So T dagger has the metric representation, which is just the Hermitian of A. Okay. Okay. And of course, that in the real case, that is the transpose of A, right? Or when. Okay. All right, so T is normal if and only if T dagger T equal to T dagger. So if and only if, so their metric representation must be the same, and that means that AH equal to AH. Okay. Or maybe I do it gradually. So okay, and then this is actually so this is A. Okay. Or Okay, so this is equivalent to saying that AH all right, and okay, so linear operator on n-dimensional Euclidean space is normal if and only if that either in the complex case we have this identity, in the real case we have this identity. Okay? So that says that so we define so that so matrix is that A is called normal. Okay. So if A is a complex matrix and A is called normal, if AHA equal to AAH. Okay. In the real case, it's called normal if AT A is equal to AAT. Okay. Okay. So we have normal linear operators, and we have normal square matrices. Okay, we have normal square matrices there. Any questions? Okay, so now spectral decomposition. If a T is a linear operator, has a spectral decomposition, right? For real case, the necessary condition is that T must be self-adjoint. For the complex case, that T is normal. So our job is to prove the reverse direction. For the complex case, we want to prove that if T is a normal linear operator, then T has a spectral decomposition like this one. And for the real case, we have to show that if T is self-adjoint, then T has a spectral decomposition. Questions? Any questions? Good. Now, a generalization of the example shows that For linear operator on n-dimensional Euclidean space, that to be normal if and only if their metric representations are normal. Okay, and this is the same for general case. So I will state it in here. So a linear operator on V is normal if and only if the metric representation B of T relative to and also normal basis for V, okay, is normal. Okay. Okay. So that is the if and only if condition. So to check a linear operator to be normal, well, you can first find an also normal basis for the n-dimensional inner product space V, and then you find the metric representation. Okay, so you have a matrix, and you check normality. Okay, in the complex case, you check that whether this is true. In the real case, you check whether this is true or not. Okay, so that it becomes to be computationally feasible. Okay, so this is a way to do it. And the proof, I think, time is limited. So it's easy, so please see the lecture notes. Okay. All right. All right, so now a linear operator T on a vector space V is called invariant on a subspace W of V. If you transform every vector in the W, you find that the image is also in W. Okay. Okay, so if you find that you can find a subspace W such that after you transform it, so the diagram is like here. So this is V, and you have a W, and you have this is T here, and you find that for every vector here, the image of T is always in W. Okay, then if this is the case, then the linear operator is called invariant. Okay, on W. All right, now in this case, all right, in this case, the restriction of T on W denoted as, okay, so restriction. So originally T is from V to V, right? Linear operator. But the restriction of T on W well becomes to W to W. Okay. And this is guaranteed because that for every vector in capital W, the image is also in capital W. Okay. So the restriction denoted is a linear operator on W here. Okay. So it's called a linear operator on W. All right, so now we are able to state the complex spectral theorem the complex spectral theorem is the to say that the converse is also true for the complex case. So when T is normal, right, then T has spectral decomposition. All right, so V is an n-dimensional inner product space over C. So it's complex. Okay, T, a linear operator on V. Okay, so we have C here. Okay, so they are complex numbers lambda 1, lambda 2 up to lambda n, not necessarily distinct. And also normal basis for V. Okay. Such that Tx, so that T has a spectral decomposition. Okay, so we have spectral decomposition if only if T is normal. Okay. All right, so I will sketch the proof. Because the proof is long. Okay, so I sketch the proof that the necessary condition has been done. So okay, so we already know that. And so now we have to prove the river directions. So now, assume that T is normal. i.e. T dagger, T equal to T dagger. Okay. So we have to assume that. And we will prove that there exists an orthonormal basis, and there are complex numbers that's such that we have this is spectral decomposition. And this is, so we will, show by induction on n, which is the dimension of the V. Okay. So we will show the spectral decomposition by induction on n. All right. So okay. So now for n equal to 1. All right. For n equal to 1, we let u be an orthonormal basis for V. Okay, because it's one-dimensional, and we prove in chapter 7 that every finite-dimensional inner product space has an orthonormal basis. Okay, so we have. Maybe I use U1, okay? So U1 is an orthonormal basis for V, okay? Now, and we know TU1 is also in V, so TU1 is equal to num.1 U1. Okay, because that every vector is a scalar multiplication of V1. Okay, because one-dimensional. So for some, okay, okay. Right, and the sinks TU since x is equal to x U1 for x in V. Okay, and the scalar is actually, so this is actually the projection. Okay, so Tx is equal to T so this is num.1. Okay, so we have spectral decomposition here, right? This is for n equal to 1. So this is the spectral decomposition. Right, so which is 1 with n equal to 1. Okay. All right, so and so so 1 is true, right? For one dimensional. And we assume 1 is true for n from 1 to up to k, with k greater than or equal to 1. Okay, so we assume. All right, and now consider n equal to k plus 1. Right, so that is the crucial point here. First one here. Now the characteristic polynomial, f of lambda, okay, of t factorize to linear factors over C, i.e. f lambda can be by the fundamental theorem of algebra. Fundamental theorem of algebra says that if you have a complex coefficient polynomial of single variables, then this polynomial will has at least one root. Okay. And so basically, if there is one root, then there is a linear factor. And by induction, by recursion, I mean, you can show that every polynomial with complex coefficient, okay, can be factorized into linear factors here. Okay, so that means that so this implies T has at least one eigenvalue. Set lambda in C. So they can be, maybe I use alpha 1. Okay. All right, because I want to reserve the lambda. All right, so T has at least one eigenvalue, lambda in C. Okay. So the existence of eigenvalue is because of the fundamental theorem of algebra. Not from the development of linear algebra. It's from algebra there. Okay, and so that we let E be the eigenspace corresponding to lambda. Okay. So there is one eigenvalue, and it must has a corresponding eigenspace. And this eigenspace, of course, has dimension at least 1, right? Okay, and for all u in the eigenspace, Tu is equal to lambda u. So this implies that this is implies that Tu is also in E. So for every U in E, the image also in E. So this implies that T is invariant. Right? So T is invariant on E. T is invariant on E. Now, okay, and so we want and also for all U in E, we look at T and T dagger U. Okay. Right? So again, we check for all U in E. And we want to know whether what is the image of U under the T dagger. Right? And because T is normal, so this is T dagger, right? And the TU. So you can exchange the order of composition. And why is that? Because U is in E, so Tu is lambda U. And by linearity, we have lambda T dagger U. What happened? T dagger U satisfies the eigen equation corresponding to eigenvalue E, lambda. So this means that T dagger U is also in E. Right? Because you can look at this as a vector, right? The image is a vector. So you can think this is V. TV is equal to lambda V. So this V must be in the eigenspace, right? All right, so this proves that. And so this implies T dagger is invariant on E2. Okay, so we have so E is an invariant space, right, under the T, and also under T dagger. Okay, it's a little bit surprised, but this is the fact. Okay. How about all right, now we let E perp be the orthogonal complement of E. Okay? Now, for all V in the orthogonal complement of E, okay, we have that so we have that TV U is equal to V T dagger U for all U in E. Okay. Okay, so I think and this is 0. Okay, so this is 0. This is okay. So TV and U is for all E, and you can see that this is 0. Why? The reason is because we just proved that this is in E. Okay? Because T dagger is invariant on E, and so for every U in E, T dagger U is in E. Okay, and the V is in the orthogonal complement, so they are orthogonal. So this is 0. And because this is 0, this is true for all U. So this is implies that T V is in E dagger. And similarly, T dagger V U, which is equal to VT U, and also 0 again. And so this is the T U for all U E. Okay, and you may think about that this should be T dagger, but this is T. Okay, sinks T dagger T. Right? In the exercise, right, you have proved that. And so this is 0 because this is in E. And the V is in the E perp. So this is implied that T dagger V is also in E dagger. All right. So this implies that both T and T dagger are invariant on E dagger. Okay, and so now we have an interesting thing here. V is E direct sum of E dagger. From chapter 7, we know that. And we know that T E is from E to E. T dagger E is from E to E. T E dagger from E dagger to E dagger. And T dagger, I'm sorry, T perp, E perp. Okay, so we have this situation now. The decomposition here, and we have the invariance, so that the restriction of T on E is the linear operator. The restriction of T dagger is also linear operator, and also also we have in E the dagger, okay, is actually equal to the E here, and T, E per. The digger is equal to E perp. Okay, it's easy to justify that we have this, all this information here. Okay, so okay, and so now the rest, once you know, because the important thing is here. This is the core of the proof. Okay, so you know this one, and so please see the rest of the proof. Okay, so I have to stop here. Right. Okay. So once you understand the invariance, then you will understand the rest of the proof of the induction. Okay. All right. So I'll stop, and you have to. Sorry for the extended time, and you.